you very much, Bartos. Thank you very much, the organizers, for this excellent opportunity to meet up with new people. I mean, at least to me, see good friends, collaborators here. It's been a pleasure, despite the high temperatures. So I'm coming from California, way too far, and I try to follow Luminita's idea about having a presentation that's going to be accessible to students. So what I'm going to talk to you about is going to be kind of an introductory component of my research. I will start with wave phenomena. That's part of my research. I study wave phenomena, Bose-Einstein condensation. We have seen many talks about Bose-Einstein condensation, superfluidity, vortices, all sorts of really interesting things that I was quite fortunate to see and learn. What I will do then is, typically when we solve those models, we are dealing with root finding problems. When we want to solve a partial differential equation, typically we end up with a large system of nonlinear equations that we want to solve. We're going to briefly review Newton's method. That's a fixed point method that under ideal conditions, it converges quadratical if you're really close to the actual root of the problem. And then we're going to extend it, and I will come back to this slightly, by incorporating some penalization methods. That's going to be what I'm going to call deflation. And also, typically, when we study nonlinear equations, we want to actually find branches of solutions as one or more than one parameters of the model changes. So we will be tracing branches of solutions to nonlinear equations, and that actually will be what I'm going to call the deflated continuation method. So we will apply this to the nonlinear Schrödinger equation. A few words have to be said for the linear Schrödinger equation, because we can gain very important information from what we call as the linear limit. It's all about solving a Sturm-Liouville problem that will tell us a lot about what suitable guesses one can use to trace solutions to this nonlinear partial differential equation. Then we're going to analyze BCs using the NLS equation, solutions in 1D and 2D, some glimpses about discovery of new solutions that have never been reported before in 2D and 3D, in 1 and 2 components, and in 3D in 1 component. And then I'm going to summarize with some open problems and current ongoing efforts of this program. So I'm studying wave phenomena. Wave phenomena are disturbances that can transfer energy. Without waves, energy cannot do anything, and without energy, waves cannot create those disturbances that can transfer in a medium. So one typical example, a droplet, a raindrop that falls on a pond, creates those disturbances that propagate through space-time. I'm quite lucky living in California, where the beach is like 10 minutes far away by car, where I'm quite familiar with those ocean waves where wind blows the surface of the ocean and creates those wind waves, as I recall, sometimes can be dangerous when, for example, a sea state can develop what we call as a rogue wave or tsunamis, among other interesting phenomena. Just for historical purposes, my background is coming from general relativity, and I have been working many years ago, when I was young and promising, on Einstein's theory of gravitation, and in fact, such type of disturbances can appear at the macroscopic level, where you have a binary system that rotates around each other. Two neutron stars can create those disturbances that can propagate through space-time, creating those gravitational waves. Have been predicted by Einstein himself, have been found in 2015, and that was the Nobel Prize of Physics for their discovery. Now, at the macroscopic level, we have light waves. A white beam encounters an obstacle and it gets diffracted, as we say. It gets decomposed in different wavelengths, different frequencies, different colors, if you like. But also matter itself can behave as a wave, not only as a particle, but as a wave. That's what we call as the particle-wave duality. It's the key component in quantum mechanics. So we have seen this slide many times. Bose-Einstein condensation, the fifth state of matter, which was predicted by Bose and Einstein back in the 20s. 70 years later, it was found experimentally by two groups in Colorado, in Gila and MIT. But for me, as an applied mathematician, what we see is that when the temperatures reach very close to absolute zero, everything becomes localized. And for us, we see such a localization as a soliton, a structure that has a finite spatial extent that we can actually study many interesting things. So when it comes to the computation of solutions that that possess wave phenomena, in principle, we have a root finding problem. One of the fundamental problems that you want to solve f of x equals to 0. So you use fixed point iterations. Newton's method is a special type of a fixed point method where your iteration function is fixed, the x minus f of x over f prime. And what it does, it generates a sequence of iterates. And as we know from calculus, a sequence iterates when the limit of xn as n goes to infinity approaches a finite number. That is your solution to your nonlinear equation. The key advantage is that you can immediately generalize Newton's method for systems of equations. That's the case when you solve PDEs, for example, that give birth to such large systems of nonlinear equations. Instead of having f prime to the power of -1, you have the Jacobian inverse times f. That is the Frechet derivative, as we call it. But in reality, numerical analysis, we do not invert this matrix. It is very expensive. Instead, we just focus on the following observation, that the action of a matrix to a vector gives you a vector. And if you multiply this equation with J, with the Jacobian, what you get is another, in my opinion, fundamental problem in scientific computing, which is the solution to a linear problem. In other words, if you want to solve a nonlinear equation, what you do is that you solve essentially a system of linear equations. Okay, that is the key advantage. Now, when it comes to root finding problems, one of the questions is, okay, I'm going to start with an initial guess. I have to know something about my problem, and I want to find a solution to it. And if I find it, I'm happy. But there is a natural question about the existence of more solutions. How can we find them? Well, something that we teach in a graduate course on numerical analysis is the idea of deflation that was introduced back in the 60s by Wilkinson himself, who said that suppose that you have k roots to a polynomial p of x, you may be able to find more roots to this polynomial if you do not solve p of x equals to 0, but you solve q of x equals to 0. So you factor out essentially the roots that you already know in this fashion. Okay? So if Newton's method converges, it will converge to something distinct. Okay? However, this idea was generalized to systems of nonlinear equations in the 70s by Brown and Gerhardt, that said, well, now the deflated problem is going to have this form, so you're not going to solve f of x equals to 0, but you're going to pre-multiply your f of x with this operator, this m, that essentially you can think of this as a repulsive potential, if I may, where if x star is known, throughout the iterations in Newton's method, this actually is responsible of departing from the x star that you already know. So this m is what I'm going to call as a deflation matrix. However, there is one danger. The danger is that if this difference is quite large, okay, you're going to have something very large, which is 0, so Newton's method might erroneously converge to the trivial solution. Okay? So you can bypass this through the idea of Patrick Farrell, Birkinson, and Funke in 2015, where they applied this idea to partial differential equations. So essentially, they played the game of adding this potential, if I may, where you can have some control on its strength, but they added also this shifting, this sigma, that are problem-dependent parameters. And the nice thing about it is that you have, if Newton's method converges, it can converge to a distinct solution. Then if you want to find more solutions, you multiply your f of x with this operator. You may find another solution, and so on and so forth. So I also have a simple MATLAB implementation when I teach this stuff, just to show you how this applies in MATLAB. So, for example, I'm going to pick a polynomial of degree 3. I'm going to pick 3 coefficients so that I have control about the roots on this problem. So let me say minus 4, minus 4, 0.2, plus 3.145. Okay? Oops. I had to do the concatenation, right? You see? There you go. So here, I'm just graphing this nonlinear function. I used Newton's method with just one initial guess. It found this root. So now I'm going to deflate this root, which means that I'm going to pre-multiply my equation with this deflated operator. So Newton's method is going to find the second one, shown with the black star. Now I'm going to deflate those two. I'm going to multiply now one more time with this new m for that solution that I found. And then I'm going to find the third solution, which is here. Okay? Of course, if I deflate those three, since there are no other solutions to my problem, Newton's method will reach the maximum number of iterations. So it doesn't converge anywhere. So if we increase the dimensionality, let's say that we have two equations. So let me do that. So when you have a system of two nonlinear equations, essentially you're looking for points of intersection of those two curves at the z equals 0 plane. So you pick an initial guess. Newton's method converges here. I'm going to deflate this one. I'm going to find a second solution. I'm going to deflate those two. 3 solutions, 4 solutions. And I can keep using it and nothing else happens. Okay, that's the key idea here. Okay, so going back now to my slides. The other important thing that we do when we solve partial differential equations, it might happen that you have a parameter in your problem. It could be the chemical potential in the Gross-Peterski equation. It could be the frequency or period if you study periodic orbits, but you have one parameter. And you want to vary this parameter and trace solutions to this nonlinear, to this root finding problem. So we use what we call as continuation methods. So those are algorithmic approaches that allow you to do that. You can trace branches of solutions. I'm going to call them X star as this parameter lambda varies. We typically use, well, there are many methods, just to be fair here. The most intuitive one is that you can use sequential continuation, meaning that you fix your parameter lambda naught. You start with an initial guess. Your Newton's method converges to x0. And if you want to find a solution at a nearby value of your parameter, let's say lambda 1, which is far away by delta lambda, you use your x naught as an initial guess for this value of your parameter, and then you're going to find the other root to your problem. And then you can keep tracing this branch. However, where you might encounter a problem here, when you reach a turning point. Because at the turning point, you're going to have a vertical tangent. Your Newton's method will not converge to anything, so you have to do something else. So back many years ago, Eusebius Dedel, Kuznetsov, and many other people came up with the idea of pseudo-arc length continuation. So now you're not going to continue over your natural parameter, let's say lambda. You're going to continue over the arc length. So the idea in 2 sentences is that starting from lambda naught and x naught, you're going to move tangentially by delta s. Okay, that is your prediction. And then you use an orthogonal correction using Newton's method in order to find this other point on your solution curve. Okay, so this idea is capable of bypassing turning points. Okay, so as an example, a polynomial of degree 4. I have a parameter lambda that I want to study the dependence of my solutions versus this parameter. So I used pseudo-arc length continuation. I just pick one guess. I found one solution, and then I used my pseudo-arc length code, and I was able to bypass this point. Of course, the question is, are there any other solutions here? You don't know this a priori. So if you're brave enough, you can start playing with different guesses. Okay, and you might be lucky, and you might find another solution, which is distinct. It doesn't belong on this branch. You use again pseudo-arc length continuation method, and then you find another branch here, which is distinct from the other one that you started with. So in that sense, pseudo-arc length continuation method cannot tell you anything about the existence of another branch. Okay, so now combining deflation and continuation, you might be able actually to find, I wouldn't say all solutions, but more and more solutions to your problem. Okay? So what does this mean? It means that given a nonlinear problem, you use Newton's method for a fixed value of lambda, you find U star, you deflate the solution, okay, which means that you solve the deflated problem, you will find another solution, so you try to deflate as many times as possible, okay, depending on what you get from Newton, and then when there are no other solutions, then you just call it a day, and you just move to other values of lambda. Okay, you just combine the idea of deflation and continuation here. So for example, here we know that we have those two branches, right? So if you pick deflation, let's say you pick an initial guess, x naught equals minus 0.1 and lambda equals minus 8. I'm just fixing lambda here. So Newton's method will converge to this solution because I'm pretty much far to this point. Okay? If I deflate this solution, I'm going to find then this solution. Okay? I'm now deflating those two. There are no other solutions to my problem. I'm reaching the maximum number of iterations in my Newton code, so I call it done. Then I'm going to start gradually increasing lambda towards positive values of lambda. So at each step, I'm going to keep deflating each solutions that we found, all the solutions that I found. At some point, when I'm going to deflate those two, I'm going to find this third one that belongs to the other branch. Okay? Then I'm going to keep increasing lambda, and then this way, I'm able to trace the other branch that is disconnected from the one that I started with. Okay? So that's the idea. Okay, now let's see how we're going to do this now for matter waves. By the way, I couldn't resist to just include this, the light diffraction, which is the cover of Pink Floyd's Dark Side of the Moon. I'm very fan of Pink Floyd. So okay. A little bit about quantum mechanics. Mathematical description of a quantum system is described by the wave function. However, I think it was Max Born who said that the modulus phi squared is the real quantity, is the realistic quantity which describes the probability of finding a particle at position r and the time t. Certainty means that if you add all those probabilities, you're going to get one, or if you integrate your density, you're going to get one. So linear Schrödinger equation, introduced 1926. It involves a kinetic energy term, a potential term. That's a standard problem that we solve in an undergrad quantum mechanics class. How we do that? We use separation of variables. We separate space and time. E is going to be the energy levels of my system, and what you get another important problem in science. It's an eigenvalue problem or a Sturm-Liouville problem, and let's see how we can do this in one dimension by using the quantum harmonic oscillator. So omega is the trap strength, if I may. So you clean up the ODE a little bit, you study the asymptotics, you see how the solutions behave far away, and then what you get a nice ordinary differential equation for this f of u. Okay, you use your series techniques that you learn in an undergrad class. You're going to find a recurrence relation for the coefficients of your power series, but you have to truncate them such that you have bound solutions, which means that you quantize the energy, and that actually will give you that the energy states of your system are quantized in this fashion, n plus 1/2 times omega. So the solutions to this differential equation, which we call as the Hermite differential equation, here I'm just highlighting the H0, the H1, the H2, those are the Hermite polynomials, which we obtain them using power series, and then we can reconstruct our eigenfunction to the problem. Now n is my quantum number, okay? So you have your eigenfunction expressed in terms of the Hermite polynomial of degree n, modulated by a Gaussian. Here I'm just showing you the modulus phi n squared for different n's, the ground state, or you can think of this as a bright bomb, as a bright soliton. The n equals 1 as a dark soliton under the presence of a trap because the tails go to 0. N equals 2, the second excited state, two dark spots there, n equals 3, third excited state, and so on. Now, this is interesting because you can actually do this, you can play the same game in 2D now. You can study this Sturm-Liouville problem by separating x and y, and nothing else. The eigenfunctions of this problem now are nothing else than a product of two Hermite polynomials in the x and y directions. You have now two quantum numbers, m and n. Okay? The eigenvalues are the sum of each direction, you get m plus n plus 1 times omega. If you prop the density, you have the ground state. The lowest energetically state is the 0, 0, the first excited state. The 1, 0 has 1, 0 crossing along the x direction. You can think of this also as the 0, 1. It's the same state. The second excited state comes into two flavors. You have the 2, 0 state, which has 2, 0 crossings. And the other possibility is the 1, 1, where you have 1, 0 crossing along the x and along the y directions. Okay? You can also study the problem in polar coordinates. So in polar coordinates, you're going to separate your radial and azimuthal part in this fashion. L is the charge of the vortex, or the winding number, as Carlos said at the very beginning of this conference. You get an ordinary differential equation for this problem. It's a Sturm-Liouville problem that you can solve. You can describe your eigenfunctions in terms of Laguerre polynomials. If you prop the density, now you have two quantum numbers again. The k describes the number of radial zeros, and L is the charge of the vortex, or the winding number. You have the ground state again. The 0, 1 is the charge with vortex 1. First excited state, second excited states can come into two flavors, the 0, 2, a vortex with higher charge, with charge 2 in this case, and here you have a state that has a ring with 0 density. Okay? So now you have a plethora of information on what is going on with a linear limit. Now in 3D you can also do that, and you can do this in Cartesian coordinates. You have now the product of those three Hermite polynomials in each of those directions with the respective eigenvalues. You can do this in cylindrical coordinates, in spherical coordinates. You have now everything you need from the linear limit. Okay? And again, we do that because at the very end, we're going to use this information to find solutions to the nonlinear Schrödinger equation. So those are your initial guesses, if you like. Okay? So in 3D, you have, from the eigenfunctions, you have a vortex line. In cylindrical coordinates, it is the 0, 2, 0. There it is. Okay? And you can have other structures, like the vortex ring, which can be constructed out of what we call as the ring dark soliton and the one dark soliton, where you have a cut at the z equals 0 plane. Okay? So we want to do that to study those type of structures. The nonlinear Schrödinger equation that we have seen in this conference, or the Gross-Pitesky equation, is not only used in atomic physics. It's kind of a universal model. It can appear in optics, in water waves. I'm going to be working with a parabolic trap, the quantum harmonic oscillator potential. Now, depending on the sign of your nonlinearity, you can have attractive interactions between the atoms, or you can have what we call as a focusing nonlinearity in optics, or you can have repulsive interactions if gamma equals +1. And the really cool thing about this problem in 1D, and also in the absence of the potential, I think we should say a few words about it, is that it is a special type of a partial differential equation because it is an integrable system. It means that it has an infinite number of conserved quantities, which allows you to construct explicit solutions by using either the inverse scattering transform or direct methods, including Hirota's method, by linear methods. There are all sorts of beautiful stuff out there. So for gamma equals -1, when you have a focusing nonlinearity, you have a minus sign there. You have the bright soliton solution, which is expressed in terms of a hyperbolic secant. Its modulus square, if I plot the spatial part of it, I have this bright bump. That's why we call it as a bright soliton. It is dynamically stable over the course of time propagation. On the other end, if gamma equals +1, you have, as I would say, the one-dimensional analog of a vortex. It is the dark soliton, and as Panos said, you have atoms on the left, atoms on the right, and the density deep here. It is a solution that sits on a finite background, which is dictated by the value of mu in the solution. So since the model is integrable, you have infinitely many ones. You have the number of atoms, which is a conserved quantity. It's coming from the U1 invariance of the NLS. You have for time and for space and time translations, you have the momentum conservation and the energy conservation as well. But when you add a trap, when you have a potential, the one that they have, the problem is that the model is no longer integrable. We're going to see how we can solve it. So separation of variables, because the problem is self-adjoint, and two limits can be actually distinguished here. One is that when the number of atoms is quite small, or the small density limit, meaning that your nonlinearity is, I can kick out the nonlinearity, and what I get is the quantum harmonic oscillator that I know everything here. I know all the eigenfunctions, I know all the energy levels, which now those are played by this mu here, the chemical potential. On the other end, if I keep pumping atoms to the condensate, it becomes quite fat, meaning that that there is no room for the atoms to move around, so the spatial translations are almost zero, meaning that your Laplacian is zero, and you get now an algebraic solution that we call it as the Thomas Fermi solution here. Okay? And of course, the question is what is happening between those two limits, between the linear, the low density limit, and the large density limit. So what one can do is use Newton's method and continuation. And we'll see later on that deflation will tell us many, many interesting things. So in 1D, the situation is neat. You start from all those linear eigenfunctions, the ground state, you do your continuation over mu, the number of atoms increases, you just reach the Thomas Fermi limit, the solution is quite fat. You can do this for the first, second, third excited states all the way to the Thomas Fermi limit, okay? In 2D, however, there are some surprises in quotes, which will come back, is that you can start with the ground state, you can continue it all the way to the Thomas Fermi limit, fine. Then for the first excited state, you have two possibilities, one in the Cartesian representation and the other one in the polar representation. So this is the vortex of charge 1, I can continue all the way to the Thomas Fermi limit, there it is. But for the 1, 0, if I do the continuation, something is happening here that gives birth to a solution that has now two vortices. And then if I keep continue this state a little bit further away, I have the emergence of another branch of solutions which has now three vortices. Okay? So those are what we call as bifurcations, which I'm going to come back in a bit, and those are pitchfork bifurcations in particular. And in order to understand them, we have to do a Bogolyubov-de Gennes analysis or a stability analysis about the stationary solution that you find. Okay? So you have your time-dependent NLS, you linearize the NLS about a stationary state, or you can linearize the Hamiltonian. As Ricardo said yesterday, you will get an eigenvalue problem of this form. Okay? So you want to calculate the eigenvalues of this matrix, and what happens is that if all those omegas lie on the real axis, your solution is stable. Instabilities can come up in two flavors. One is if they're pairs of purely imaginary eigenvalues, or as quartets. In this case, you have exponentially unstable solutions. They grow exponentially time, far away from your equilibrium point, or they can perform oscillations with growing amplitude. Okay? So what we did then in 2018 is that we use deflation now to just try to find more and more solutions to this problem and analyze the stability and understand the potential bifurcations that we saw that may exist in this problem. So first of all, we benchmark the method. So what we found is that, well, first of all, we pick the ground state, we continue it all the way to the Thomas Fermi limit, let's say up to mu equals 1.32, if I remember correctly. We use that solution to the deflation algorithm, we found the second solution. We deflated those two, we found the third solution, fourth, fifth, and so on. The first thing that one does is we want to understand out of those solutions that we found how, I mean, are those solutions known or known? So we benchmarked the method and found essentially solutions that are known to the literature, this picture that I showed you previously. And what happens essentially at those 2 points is the following thing. So you have if you monitor the eigenvalues of the parent branch of the state having one stripe along the x direction, here what happens is that you have a pair of real eigenfrequencies, as we call them, that collide at the origin, creating an instability, meaning that the parent branch is stable. Then at this collision, the parent branch becomes unstable, and the daughter branch, the branch that emerges from that one, which is the vortex dipole, inherits this stability. This is the exchange of stability here, okay? So later on, a same bifurcation happens later on here. You have one more zero crossing that gives birth to a vortex tripole here, okay? Those are peaks for bifurcation. So one simulation about the situation here. So let's say that you pick the unstable stripe solution here, and if you evolve it forward in time, the dynamical system will try to approach a nearby stable solution, which is the solution that has two vortices. Okay, so the problem, so the model prefers to create those vortical patterns. So in total, in one component, in 2D, we found up 63 solutions. Many of them can be classified in terms of the linear limit, so that is why it is important to know how those solutions look like at the linear limit and how we can describe them, including 50 new ones. So those 50 new ones are shown here. Well, a subset of those, including a bifurcation of the solution that has 1, 2, 3 stripes. So essentially I have it here as well, a solution that has 1 stripe and 3 vortices on the left and on the right. Okay? So one more video that the system prefers to create those vortical patterns. If you start with a ring, oops, I think it should be shown here. Yep. So let me go back. So if you start with this solution that has a ring of 0 density and evolve it forward in time, you have the formation of those vortices and then those disperse. Okay? So we got really excited about this problem, and we now consider the two-component NLS in 2D. So I think Janos mentioned about the such a setting, in particular in 1D, and in the absence of an external potential, the model is integrable if you have equal interaction coefficients. That is the so-called Manakov model. But in the presence of a trap in 2D, the model is not integrable, and what happens is that one component creates a potential, an effective potential to the second component, so that you can trap bound modes in phi plus, as they call it. So same setup, you separate variables in space and time. You have now 2 chemical potentials. You fix the mu minus, which is the potential of the chemical potential of the first component. And you use mu plus as your continuation parameter. Okay, so some solutions here. This is a bright soliton and a stripe, a dark bright bound mode, if you like. Here I'm showing you the eigenfrequencies as a function of mu plus. The solution is stable at the very beginning, and then you have this bubble, and then there is a 0 crossing that happens somewhere here, which actually corresponds to the emergence of another state that has 2 vortices. I mean, we have seen this in the one component setting. Remember that it was the stripe that gave birth to a solution that has 2 vortices, 3 vortices, and so on, through those pitchfork bifurcations. So the first one gives birth to this solution. Later on, there is one such pitchfork bifurcation later on, giving birth to the vortex tripole here in the second component. Other states, a solution that in the second component has this ring with 0 density, more bifurcations that emerge as we vary the mu plus. One gives birth to this state that has 2 stripes here, and this itself has one such 0 crossing that gives birth to such a state. The parent branch also has one secondary bifurcation that gives birth to this solution that has 1, 2, 3, 4, 5, 6 vortices in the second component, okay? But totally unstable. Okay, so the bifurcation diagram, the coloring, maybe I didn't mention that, but just that the blue line is solid, that the solid blue line is stable solutions, red and green exponentially and oscillatory instabilities. Also, another interesting diagnostic is that if you monitor the total number atoms difference with respect to a reference state, you can actually pin down exactly where those solutions emerge. Now, something else that I wanted to highlight here is that when it comes to the computation of the spectrum of the linearization, or when you carry out the BDG, as we call it, the Bogoliubov-Dezhens analysis, is that I encountered a problem. Maybe I was too ignorant back then, maybe I was, and it is the following. Without using any special techniques like shift invert or all other stuff, I solved the problem for the 2-component in MATLAB using EIGS. It is a sparse eigenvalue solver. You parse your metrics, you compute the spectrum, and what you find, I mean, in this particular case, I found a mess. This is a mess. So the mess is due to the following fact. That's something that I keep telling my students, is that when you solve a problem numerically, make sure you plug everything back to the computer and see whether it satisfies the problem that you're trying to solve. Okay, it is important. So by doing this, if you just monitor, let's say, some sort of a relative error of your matrix A, your that appears in the BDG with the right eigenvectors and the eigenvalue that you find that the error is quite large. So that kind of explains this mess. Okay? So that took me a lot of time just to figure out what to do next. And thanks to Hans Johnston, who was sitting next to me back at UMass Amherst, he said, well, there is this multi-precision toolbox in MATLAB called AdvanPix that you can actually extend the precision in your calculation with the hope that you will be able to resolve better and better your computation. By the way, the reason for doing this is that if you compute the condition number of this matrix A is 10 to the minus 18 or something. It's very large. It's very ill conditioned. So by doing that, I was able to compute 100 eigenpairs with an extremely good accuracy. But if you want to compute the entire branch, which consists of 121 solutions, that took something like 3 months, and I had, I think, many branches to do. So I think I would be close to retirement to get this done, I would say. So thankfully, however, when I was at UMass, I was aware of Eric Polizzi, shown here, who had developed in 2009, a few years before my arrival at UMass Amherst, he developed an eigenvalue solver called FIST. And what it does essentially in one sentence is that you prescribe a contour on the complex plane, and you're trying to find all the eigenvalues inside this contour. Okay? It has been benchmarked in many problems, including ill-conditioned problems. It has all sorts of features that one would want to, parallelization, everything. So by doing this computation for the entire branch, it took me like 20 minutes or something. So I was able to compare what I did with extended precision and with FIST quite well. I mean, the comparison is perfect. Okay, just to highlight that. Now, in 3D, I think I have another 13, 20, 12 minutes maybe. Yeah. For the 3D case, one component, just a few snippets of results, is we use the deflation method for this problem, and here are some solutions that we found. The planar dark solid with a vortex line piercing the condensate, 2 vortex lines, a vortex line star, 4 vortex lines, 2 vortex line handles with a vortex ring connecting those two, and 2 vortex lines that are interconnected with each other, and some dynamics that I would like to show you for the vortex line and vortex ring handles, that the solutions are unstable, weakly unstable, I would say. And now what we're going to see is that something that I saw in this conference is all these reconnections of vortex lines. So that's what's going to happen in a bit. Those will split into vortex lines. They're going to reconnect. They're going to split. They're going to reconnect. And this pattern keeps going on and on. Okay, so now they're going to split. They're going to reconnect. They're going to split. They're going to reconnect, and so on and so forth. Okay? This is time, yeah. So you have found the stationary solutions to the problem. You have studied the spectrum, and then you just evolve them forward in time and see what's going on. Yeah. More complicated solutions, another vortex line star. Here you have 2 vortex rings. On top you have 1, 2, 3, 4 vortex lines, and then a vortex line perpendicular to that structure. Here you have an S-shaped vortex line with a vortex ring here, and more complicated vortex line structures. And just 2 videos. Let me see. Yeah, so that's the structure which has 1, 2, 3, 4, 5 vortex lines and 2 vortex rings in between. So now those will split. They will reconnect, split, and reconnect. Yeah. So, and one more. This is a vortex line in an S-shaped form, and the vortex ring connecting the whole structure, and you have those handles here and there. So as time passes by, those vortex lines will split, and then they will reconnect. quite cool findings. So, okay. One bifurcation that we found was this state that comes from that one. So the deflation and continuation, this couple technique is quite interesting to be applied not only to this problem, but there are so many other problems that one can use it. So quite recently, a work that we did with Panos and Ricardo, Mithun and David Hall. Ricardo yesterday mentioned David, who is an experimentalist at Amherst College. We studied a three-component problem and extending pseudo-arc length, but now using iterative solvers therein. In MATLAB, we were able to also trace a bifurcation there, a saddle center bifurcation that corresponds to essentially two half quantum vortices called Alice rings that were found using pseudo-arc length. So what you have a plethora of tools that you can use in order to analyze the configuration space of such interesting partial differential equations. So I think I'm going to start summarizing here. The tools that we have for bifurcation analysis, the existing tools may fail to detect disconnected branches of solutions. I presented you a method that can become robust, can become effective, even better, to discover solutions, new solutions, and what we're interested in, we want to see where those solutions are coming from. Are they coming from the linear limit or bifurcations? What is going on? So the purpose that I'm here in France, in Rennes, thanks to Ionut, is to incorporate and develop those bifurcation tools in FreeFEM++, and thanks to Georges, I have been taking small incremental steps towards this direction. To just tackle such, I would say, computational intensive problems, especially with the recent developments that Ionut and Georges and Victor Kalt that did, and Pierre Jolivet, using the parallel version with domain decomposition techniques. It will be quite promising to just unravel many solutions. Now, something that came up actually the last days here in this conference is that there might be a possibility to translate a code that it is written in Fortran and also in MATLAB, a linear solver, the IDRS, because remember that when you do Newton's method, you solve a system of linear equations. It might be nice to see how this works in this problem, but for now it has been reported that from the developers that the IDRS, as we call it, it outperforms the BiCG stuff, so it would be something nice to have it in FreeFEM as well. Maybe if we have time this summer, maybe we actually will play with integrating FIST, this eigenvalue solver, although now FreeFEM is hooked up with PETSI and SLEPSI, but maybe that would be something really cool to just see how we can study the problem by using other types of techniques and benchmark and see what is best for this problem. Personally, I don't like knobs, so no shift invert. I mean, there is no to me information about how much I'm going to invert, or how much I'm going to, by what amount I'm going to shift my spectrum. I don't know that. So it works fine, but I like something that it is knob free, in my opinion. So we're going to keep doing this throughout the summer, motivated by experimental results by David Hall. So here is an actual experimental setting, experimental results in a 5-component system. So you have now five GPs, 3D, quite computational intensive. And at this point, I think I would like to thank my collaborators, Panos Kevrekidis, who is in this audience. I want to express my thanks to him throughout the years. And I think he's the reason that I'm in the US, by the way, from the get-go, Pano. David Hall, our experimental collaborator with Ricardo, Patrick Farrell, Nicolas Boulet at Oxford University. Now Nicolas is a postdoc at Cambridge University. Mithun Tudiyangel, who recently moved to India. Avad Saxena and Fred Cooper at Los Alamos Laboratory, where those techniques can be applied to problems that involve people at national labs. Ionut and Georges Sadaga, definitely at the University of Rouen. Pierre Jolivet, who is the person who actually connected slips in PETSI to FreeFEM, and Boris Malamud for many inspirational discussions and scientific ideas. So I would like also to thank the funding sources, the NSF. There is a grant for a different topic, again, which has with blow-up solutions, collapse solutions, and also the support by the CNRS, which actually funds my visit in France. So here are some references. I talked to you about the first 4 papers. There are more papers on that direction with many other friends that appeared recently in 2 components, in 1 component, and so on, and some other works that revolve about computation of periodic orbits, stationary states, to other types of NLS systems, and so on. So with that said, I would like to thank you very much for your attention, and I will be happy to answer any questions you may have. Thank you.